Section 7-1, Introduction to Finite Decimals. In this section, we're going to talk about the basics of decimal numbers, and talk about some phrases that we use to talk about decimals, as well as ways to represent them. The decimal point, interestingly enough, is a way that the United States separates whole numbers from parts of whole numbers. But in fact, other countries don't use the same notation as us. For example, England uses a point, but it's centered, so it's not all the way at the bottom like our decimal point is. And Germany uses commas. So the decimal point is kind of unique to the way that we write our numbers. It does separate the whole numbers from the parts of whole numbers. We called these fractions in the last section. We use the word and to read a decimal number. For example, the number we see on the screen, the dollar amount, $128.95. A lot of times you're going to hear an extra and when people say these numbers. That's actually incorrect. I don't want to nitpick, but we don't say $128. We say $128.95. So the and is an indicator that you are introducing a part of a whole number. That same dollar amount can be represented as a mixed number, for example, where we have 128 as the whole number and the 95 cents is 95 over 100, because we know that there are 100 cents in $1. So that 0.95 is talking about we have like 95 pennies, but we actually need 100 to make it a full dollar. Because we are in the base 10 Hindu-Arabic numeration system, when we move to the right of the decimal, we are actually continuing that base 10 pattern. So if we remember, the ones place was 10 to the 0 power, so that was ones. Then when we moved up to the tens place, of course that was 10 to the first power. 10 to the second power was the hundreds place. And we kept going. But now we're talking about introducing a decimal and then continuing to the right so that we can talk about the place value names that are to the right of the decimal. So if we're following this pattern, every place value is going to be some power of 10. Now if we start from our furthest left, we're at 10 to the second power. We go 1 to the right, that's 10 to the first power, so the exponent is decreasing. Go to the right again, that's 10 to the 0 power. Go to the right again. We know that the next number smaller than 0 would be 10 to the -1 power. Continuing that pattern, after -1 becomes -2, after -2 we have -3, and so on. And we learned in the last section that negative exponents actually represent fractions, so if we rewrote 10 to the -1 as a fraction, we could write that as 1 over 10. So that place value, immediately to the right of the decimal, we're going to call that the tenths place, because it is a part of a whole, and the number of pieces that we need to make a complete whole and that place value would be 10. So we have tenths. One further, we have 10 to the -2. We can rewrite that as a fraction to be 1 over 10 squared. But remember that 10 squared is 10 times 10, or 100. So that place value we're going to refer to as hundredths. Maybe you notice a theme here. The place values are all ending in THS because we're talking about fractions. One further over, we have 10 to the negative 3. That can be written as 1 over 10 cubed. 10 cubed is 1,000. This fraction is 1 over 1,000, so we're going to refer to this as thousandths. And again, that word's ending in THS. Notice that these place values have similar names to the whole number place values that are on the left of the decimal. The difference, though, is that to the right of the decimal, we're talking about parts of numbers. And the denominator is what tells us the name of the place value. So one position to the right of the decimal, we are at 1 over 10. That's tenths. Moving over 1 over 100, that's hundredths. 1 over, we're 1 over 1,000, that's thousandths. If we continued, after 10 to the negative 3, for example, we would be at 10 to the negative 4. We could rewrite that as 1 over 10 to the 4th power, which is actually 10,000. So that place value would be 10 thousandths. So maybe we see a pattern here that we are naming the place values based on the denominator of the fraction that belongs there. And it's still following in line with our base 10 numeration system that we learned about back in chapter 3. We just saw a connection between the place value names in our decimal system and fractions that those place values get their names from. Because there is this connection, we can easily switch between fractions and decimals. For example, we have 25 over 10. And if we wanted to convert this fraction into a decimal, the first thing that we're going to do is rewrite the numerator in expanded form. Now, expanded form, remember, that's where you take a number like maybe 7,642. I can rewrite that in expanded form by looking at each of the place values. So 7 is in the thousandths place value, so I would multiply 7 times 10 cubed. Add to that, 6 is in the hundredths place value, so that's 6 times 10 squared. 4 is in the tens place, so it would be 4 times 10 to the first power. And then 2 is in the ones place. I could write 2 times 10 to the 0 here, but I'm going to leave off the 10 to the 0 because I know anything to the 0 power is 1. So this is expanded form. It's the same number. We're just expanding it out so that we can see each digit and the place value that that digit is representing. So we're going to start by writing the numerator, 25 over 10. We're going to take the numerator and rewrite that in expanded form. So 25 becomes 2 times 10 plus 5. And then the denominator over 10, we're going to leave that over 10. And then because we have an addition in our numerator, we're going to separate every term. So we have a term here and a term here. We're going to separate every term so that each term is in its own fraction. And of course, we're going to copy the same denominator over. And basically, we just reversed an addition problem. If you had started with these two fractions being added together, because they have a common denominator, you would simply add the numerators. So because we saw terms added together in the numerator, we were able to reverse that and create two separate fractions. Now, one of these fractions can be simplified. We have 2 times 10 over 10. Because that's factored in the numerator, we can divide off the tens. That would leave us with 2 over 1, or 2, and 5 over 10. So we have 2 plus 5 over 10. And 5 over 10 is actually the same thing as 5 times 10 to the negative 1. So we have 2 plus 5 times 10 to the negative 1. We know that 10 to the negative 1 is the tenths place, which means that the digit multiplying to that 10 to the negative 1 needs to be right next to the decimal point, directly to the right of that. So this 5 needs to go directly to the right of that. So in other words, 5 times 10 to the negative 1, that's the same thing as 0.5. So we're having 2 added to 0.5. That would become 2.5. Now, did that feel completely drawn out? Absolutely. But we wanted to take tiny baby steps so that we could see the connection between a decimal like 2.5 and a fraction like 25 over 10. Because those two numbers are literally the same value, but they look very different. Let's try another one. We have 56 over 100. So we'll start by writing 56 in expanded form, and then we'll put the denominator underneath that. And we're going to go ahead and separate our terms in the numerator. So 5 times 10 is one term, 6 is the other term. Each term is going to become its own fraction with the same denominator of 100. And then we're going to try and reduce anywhere we possibly can. 5 times 10 over 100. Well, I know 100 is 10 times 10, so if I consider it in factored form, I can see I have a common factor of 10. So that would leave me with 5 over 10 for the first fraction, plus 6 over 100 for the second one. And let's go ahead and look at those as a digit times the place value. So 5 times 1 over 10, and 6 times 1 over 100. 1 over 10 is our tenths place. So if we were looking at a decimal, the 5 needs to go directly to the right of the decimal in the tenths place. And then the 6 is in the hundredths place. 1 over 100 is 2 digits after the decimal. So the fraction 5.6, sorry, not point, the fraction 56 over 100 is equivalent, exactly equal to, the decimal 0.56. And we can say the number the exact same way, regardless of which notation we're looking at. In the fraction form, 56 over 100, I would still say 56 hundredths. In the decimal form, 0.56, I would say that the same way, 56 hundredths. Now, something to notice is that a couple of these fractions could have simplified. For example, 25 over 10, I know 25 is 5 times 5, and 10 is 2 times 5, and we could have reduced this. Whoops. Yeah, that's right. So that would be 5 over 2. However, this is not the process that we're trying to execute. We are looking for a way to connect a fraction notation to decimal notation. So the goal here is not simply to find what decimal is equal to 25 over 10. That's part of it. The goal, though, is to see the connection between the way that we write fractions and the way that we write decimals. There's this kind of translation that's happening, and it's tiny little mathematical, logical steps that are taking us from one notation to the next. Let's do one more. 205 over 10,000. So again, we'll start by writing our numerator using expanded form. I did put a placeholder 0 in there for the 10 to the first power. We don't have to have it though. It would have been totally fine to write 2 times 10 squared plus 5, because those give us the same values. And then our denominator is 10,000. And we'll separate each of the terms to become their own fractions. And then we'll try to simplify. Maybe you've noticed that the number of zeros in these powers of 10 is totally related to the exponent on 10. So 10,000 has 4 zeros. It's exactly equal to 10 to the 4th power. 10 squared divided by 10 to the 4th, that's going to leave us with 10 to the negative 2. Subtracting our exponents, 2 minus 4 gives us negative 2. And remember that the digit multiplied to that place value is a positive 2. And then we're adding to that 5 over 10,000. We could write that as 5 times 10 to the negative 4. Now, we have used our fraction notation here to help us see the name of the place values, but I also want to show you that leaving it written with these negative exponents can really help with placing the digits in the appropriate place value. For example, I know that there's no whole number part to this number because there's no 10 to a positive exponent terms. So it'll be 0 followed by a decimal, and then I see 10 to the negative 2, so I know that I'm going to put a digit 2 places after the decimal, and the digit I'll put there is the number 2. Then I see 10 to the negative 4, so 4 places after the decimal. We have 1, 2 already, 3, 4. The digit that I'll write there is the 5. Now, it's really important that we didn't just put 0.25 because that's not the same number that we're dealing with. We have to see that there are missing place values. And remember that zeros will help us preserve the value of a number by inserting zeros into these place values. So 205 over 10,000 is the same as the decimal 0.0205. And either way you write it, we would say that number 205 10,000ths. We just did some pretty convenient examples of converting fractions to decimals where the denominators were perfect powers of 10. But that doesn't always happen. There are fractions out there with denominators that aren't 1 with zeros behind it. For example, 7 over 2 to the 6th power. 2 to the 6th power, if we type that into a calculator, in case you were wondering, is not a perfect power of 10. It's equal to 64. But we're going to leave it as 2 to the 6th for now because the goal is let's turn this fraction into a fraction with a denominator of 10. Now we know that 10 comes from multiplying 2 times 5. So if this fraction currently has 6 factors of 2, it's missing the 5s that pair up with each one of those to make 10. So I'm going to multiply by 5 to the 6th on top and bottom so that I can create in my denominator 2 times 5 to the 6th power. That's good because that would be 10 to the 6th power, and that means we just moved ourselves into the direction of being able to recognize the place value a little more easily. 2 to the 6th power, I have no idea what place value that is. 10 to the 6th power, I do know that that is in the 100,000ths place value. And remember that the 6 exponent secretly tells you exactly how many zeros are following the 1. So 10 to the 6th is 1 with 6 zeros behind it. Going on, we need to multiply out our numerator. 7 times 5 to the 6th power becomes 109, 375, and that is over 10 to the 6th power. We'll write our numerator in expanded form. 1 is in the 100,000ths place value. That is the 10 to the 5th power place value. So we'll have 1 times 10 to the 5th plus 0 in the 10,000ths place value. Not important, so we'll skip it. 9 in the thousandths place value would look like 9 times 10 cubed. 3 in the hundreds becomes 3 times 10 squared. 7 in the tens place becomes 7 times 10, and 5 is singles, so there is no multiple of 10 there. Each one of these terms is going to become its own fraction with a denominator of 10 to the 6th power. Then we're going to go through and simplify where we can. So 10 to the 5th over 10 to the 6th, the denominator has 1 more than the numerator, which means that fraction turns into 1 over 10. 10 to the 3rd over 10 to the 6th, there are 3 more in the denominator, so there's 10 cubed left in the denominator, and the 9 carries down. 10 squared over 10 to the 6th, we have 4 more in the denominator, so that'd be 10 to the 4th, 3 on top. 10 over 10 to the 6th, we have 5 more in the denominator. And then lastly, there's nothing to reduce in the 5 over 10 to the 6th. Now remember, these exponents are telling us exactly where the digits belong to the right of the decimal. There are no whole numbers. Each one of our digits is part of a fraction, so we know there's a 0 for the whole number part, a decimal, and then we have a 1 in the tenths place. We do not have a fraction with 10 squared in the bottom, so that would be 0 in the hundredths place. We have 9 in the thousandths place, 3 in the 10,000ths place, 7 in the 100,000ths place. Oh, I think I skipped a number. We have 1 in the tenths, 0 in the hundredths, 9 in the thousandths, 3 in the 10,000ths, 7 in the 100,000ths. I think I must have said 10 to, oh yeah, I did. Earlier, I think I said 10 to the 6th is, or if I didn't say it out loud, I thought it. I was thinking that was 100,000ths, but it's actually 1,000,000th. That's the millionths place value. So we're going to have a 5 in the millionths place value. So the fraction 7 over 2 to the 6th power is equal to the decimal 0.109375, which we could read this as 109,375 millionths. What a number. Lots of people say they like decimals better than fractions, but that was a heck of a lot easier to say 7 over 2 to the 6th than to read that number, right? Often you'll hear people just read the digits, 0.109375, because saying 109,375 millionths is a mouthful. Continuing on. So this next fraction, we do have factors of 2 and factors of 5, but notice that we don't have equal numbers of each. So what we're going to do is supplement. If we have 3 factors of 2 and 4 factors of 5, we can see that we're missing a factor of 2. So I'll multiply top and bottom by 2. That way we have 2 to the 4th times 5 to the 4th, which we could write as 2 times 5 to the 4th. And we know 2 times 5 is 10, so that looks like 10 to the 4th in the denominator. We haven't done anything else to the numerator, so I've just copied the 2 over. Because this is the only fraction and there's no extra terms in the numerator, we're pretty much done. We just need to figure out where the 2 belongs. We can tell it's part of a fraction, so it does not belong to the left of the decimal at all. We have a 0 to the left of the decimal. To the right of the decimal, I see 10 to the 4th and nothing else. So that means 4 digits to the right of the decimal, I need to put a 2. Everything between that 2 and the decimal should be zeros for placeholder. Let's do another one. We have 1 over 25. Now, we could multiply 25 up to be some power of 10, or we can break it down and then look for what we need to create groups of 10. I know 25 is 5 squared. And because I know that, I can see that if I had 2 factors of 2, I would then have 5 times 2 squared. So I just multiplied the right number of 2's so that they can pair up with the 5's. That way I can create 10 in the denominator. And then I have 4 in the numerator. This decimal has no whole numbers, so it would be 0 to the left of the decimal. And then I see 10 squared, which means the digit attached to that fraction belongs 2 digits after the decimal. So I'd put a 4 here, and I need a 0 placeholder. One more. So we have 7 over 250. I'm going to factor 250 to be 5 squared times 10. 5 squared needs a pair of 2's to become another factor of 10. So I'll multiply by 2 squared over 2 squared, just like we did in the last problem, so that I can have 5 times 2 squared times 10. I have 7 times 4 in my numerator. I have that 10 squared times 10 in my denominator. I can write that as 28 over 10 cubed. 28 in expanded form looks like 2 times 10 plus 8. Each one of those terms can be written as a fraction over 10 cubed. I can simplify that first term, 2 times 10 over 10 cubed. That simplifies to be 2 over 10 squared. And 8 over 10 cubed does not simplify. There's no whole number part, so I have 0, decimal. 10 squared tells me the 2 goes 2 digits after the decimal. 10 cubed tells me the 8 belongs 3 digits after the decimal. And I can see that I need a 0 placeholder in the 10th place. So again, remember that the goal here is not simply to find the decimal number. We're practicing understanding the connection between the fraction notation and the decimal notation. You may have already realized that you can type these fractions into your calculator and use the approximation or the fraction to decimal button to find the decimals. That's wonderful. However, understanding the bridge that takes you from one notation to the next is super important. So take the time to write these out in expanded form and digest how we know where to put each of the digits.